Here we have the graphs of the squaring function, the cubing function, the square root function, and the cube root function. And as you recall, the domain of the squaring function, the cubing function, and the cube root function are all real numbers. And the domain of the square root function is the interval from 0 to infinity, including 0. Quick use of the power rule will tell us that the derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of the square root of x is 1 over 2 times the square root of x. And the derivative of the cube root function is 1 over 3x. I'll write it as 1 over 3x to the 2/3. I want now to consider the domain of the derivatives. The domain of f prime of x equals 2x is all real numbers. For f prime of x equals 3x squared, the domain is also all real numbers. Something different happens with the square root of x because we have 1 over 2 times the square root of x. That square root of x in the denominator says that the domain of f prime for the square root function does not include 0, right? So it's 0 to infinity, but open at 0. And then likewise for the cube root function, its derivative has an x in the denominator. And so its domain is all real numbers not including 0, right? So the set of x such that x does not equal 0. I want to look in particular at where a derivative either is equal to 0 or doesn't exist. For both the squaring function and the cubing function, we see that f prime of 0 is equal to 0. F prime of x is 2x for the squaring function. F prime of x is equal to 3x squared for the cubing function. And we can see that both of those are equal to 0 when x is equal to 0. Further, f prime of 0 does not exist for the square root function or the cube root function because 0 is not in the domain of either of those derivatives. This is leading to a definition, but before I get there, I'm just going to wrap it up. 0 is in the domain of all of these functions, and for 2 of them, f prime at 0 is 0, and for 2 of them, f prime of 0 does not exist. Those are the criteria for something that we call a critical number. A critical number is a number that is in the domain of f, and at that number, f prime is equal to 0 or f prime does not exist. We care about critical numbers for various reasons, but you'll note that when we look at f of x is equal to x squared, that critical number is a point where we have a horizontal tangent, right? And that horizontal tangent is associated with a minimum for the function. For f of x equals x cubed, we also have a horizontal tangent there. Of course we do. The derivative is equal to 0. It's not associated with a maximum or a minimum, but there's a horizontal tangent there. Where the derivative does not exist for the square root of x and for the cube root of x, you'll note that the tangent line is vertical. It has a slope that's undefined. You see these derivatives are undefined at x equals 0. So a critical number can be associated with a local maximum or a local minimum. Not always, as we see with the cubing function, but sometimes. I want to give you a few more examples of, well, actually a couple more examples of where we might have a critical number, and then one where we don't. For a function with a jump discontinuity at c, c would be a critical number. And for something like the absolute value of x minus c, c would be a critical number because the function is not differentiable there. But for something like f of x is equal to 1 over x minus c, since the domain would be the set of x such that x does not equal c for the function, when I differentiate it, which using the power rule would be would give me f prime of x is equal to negative 1 over quantity of x minus c squared, even though c is not in the domain of f prime, since c is not in the domain of f, c is not a critical number for this rational function.